Breaking news from the cold edge of the sun's influence. 3i Atlas is no longer playing by comet rules. In the last few days, as it slid inside the invisible boundary where sunlight starts turning ice to gas with a vengeance, this interstellar interloper brightened faster than the models said it could, grew an atmosphere that dwarfs planets, shifted to a toxic emerald hue, and most unsettling of all, threw a spear-straight plume toward the sun. That last trick shouldn't happen if radiation pressure is doing what every physics textbook says it does. Yet here we are. It is now barreling along a track that will skim past Mars and dive toward perihelion on a timetable we can't slow down, demanding answers at a pace that insults our comfortable theories. If you care about the boundary between what we think space does and what it actually does, don't blink. You're watching a live postmark from another star system. We'll walk through what changed, why the math screams interstellar, what the timeline says is about to happen, and what that sunward tale could mean when alien chemistry wakes up in hard vacuum. Stay to the end for the implications, if it fragments, flares, or quietly ghosts us after the solar flyby. This is part 1, the ignition phase, what's getting brighter, why the numbers are misbehaving, and how a tiny nucleus can throw a planet-sized atmosphere into the dark. The light curve is supposed to be your friend. For comets, it's the heartbeat. A smooth, rising slope as sunlight warms ice, drives gas outward and drags dust into a soft shell we call the coma. Predictions plug in distance, typical volatile inventories, a best guess nucleus size, and you get a nice conservative forecast of how bright the thing should get at each step in. 3. Atlas just jumped the guardrail. In mid-September, the reported magnitudes that should have idled around the mid-teens began sliding down to 12-14. Remember, smaller number, brighter comet. That's not a subtle nudge. That's a step function. A 2 magnitude drop means roughly 6 times more light. A 3 magnitude drop is about 16 times. There are only a handful of ways to do that. 1, ignite more surface area than expected. 2, blow out a lot more dust. Or 3, flip over a lid on subsurface volatiles, so pressurized gas vents, like a ruptured hydrant. The gradual warming story doesn't give you that kind of acceleration. A buried reservoir does. Now, quick reality check. This isn't about danger. Closest approach to Earth never gets silly. It stays well beyond 1 AU, with the real action happening inward and off to our side. The alarm is purely intellectual. We're watching foreign chemistry light up in real time. That matters because comets are formation fossils. They lock up the temperature, pressure, and bulk composition of the nursery where they froze. When something from someone else's nursery strolls in sputtering green and spitting dust sunward, you take notes. The trigger distance was telling. At about 2 astronomical units, a lot of comets flip from mostly CO2 outgassing to water begins to matter because the solar heat budget finally reaches the shallow ice. 3i Atlas didn't just hand over the baton, it threw a parade. Gas velocities ticked up, the coma ballooned, and the light curve bent like it hit a new fuel stream. Translation: either the crust cracked open, exposing fresh volatile strata, or we've got a nucleus laced with super volatiles primed to go off at lower temperatures than our local catalogue would lead us to expect. If you've been burned by comets before, you're already thinking about the fake-out outburst today, coma collapse tomorrow. Fair. Many comets overperform briefly and then settle down or shatter. The difference here is continuity. The overperformance persisted night over night. That takes sustained gas production, not a single sneeze. Let's ground the hype. The designation 3i Atlas is not a marketing name, it's a sentence. 3i means the third confirmed interstellar object. Atlas credits the survey system that clocked it. Interstellar isn't a vibe, it is a velocity problem. If the orbit fit comes back with a hyperbolic eccentricity greater than 1 and a hyperbolic excess speed that refuses to die even after the sun has had its tug, the object is unbound. It came from out there, and it's leaving forever. You don't book a return ticket on that math. With the first two visitors, we learned humility. One I/Oumuamua, that slender enigma from 2017, refused to outgas in a way we could see, yet it accelerated like something lightly pushing it. 2 I/Borisov, in 2019, looked like a comfortingly normal comet, but carried a chemistry set skewed toward carbon monoxide compared to our backyard norms. The lesson Interstellar isn't a type, it's a category error. Each one is a different animal. 3. Atlas continues the tradition by mashing the gas on activity early and rewriting the geometry of its dust. You can fit the hyperbola, you can time the solar swing, you can swear on Kepler's grave that the energy budget doesn't close for capture, and you'll still be left with a gritty, green, sun-facing plume that asks whether our radiation pressure pushes dust away. Story is the full story. The practical takeaway is sobering. We get one pass. There is no next apparition in 30 years. There is no follow-up mission that meets it again on the outbound leg in some tidy circular orbit. Everything you learn now, with the instruments already flying and the telescopes that can still point close to the sun without committing suicide. Dates matter here, so let's lock them in. The Mars encounter is the first real gate. Early October, on the order of 30 million kilometers in passing range, close enough that Mars orbiters designed for geology and aeronomy may be able to steal a look at the coma or even pull spectra off it if the brightness holds. That's a gift, because as the red planet gets its chance, Earth loses its grip. Solar elongation, the angular separation between the comet and the sun, drops into the pain zone, 20 degrees. 15. You can be a billion-dollar telescope with adaptive optics and a support team that drinks black coffee for fun. The sky background still wins when you drive that close to the sun. Perihelion follows late in October, safely outside the orbit of Earth, but deep enough that the sun becomes the entire story: heating, chemistry, structural stress. We will almost certainly be blind from the ground during the peak. If you're trying to design a villain arc for an object that doesn't care about us, that's how you'd write it. All the important plot points happen behind the curtain. Once it whips around, the elongation slowly improves. If 3I Atlas survives, November into December becomes reacquisition season. By then, we won't be asking, did it outgas? We'll be asking, how much mass did it lose? What did the dust do? Did the color change stick? Did any fragments decouple? And does it look like the same object we were measuring in September? Motion-wise, expect silly numbers. Hyperbolic visitors don't creep. 60 plus kilometers per second is realistic near perihelion. That's twice Earth's orbital speed. Imagine trying to sketch a portrait of a peregrine falcon that refuses to stop stooping. Except the falcon is shedding a planetary atmosphere as it dives and you aren't allowed to face the sun while you draw. Let's talk scale. Comet can get big. Many comets wear atmospheres dwarfing planets, while they are otherwise piddly little boulders. 3I Atlas has leveled this up. Remote infrared measurements point to a carbon dioxide heavy coma extending hundreds of thousands of kilometers. Park Mercury's orbit inside that, and it fits with room around the edges. Wrap that around a nucleus probably measured in single-digit kilometers, and you get a sense of the ratio, a sand grain belching a football stadium fog. Why CO2? Because volatile inventories are not universal. Our Oort cloud and Kuiper belt stock different blends. But local comets tend to be water-led. Water dominates their gas production inside a few AU. CO2 plays second fiddle in most of our examples. If a comet formed farther out around a dimmer star or in a disk with a different CO mix, carbon dioxide can freeze out where water stays vapor. Lock that chemistry in, kick the object out into interstellar space, let it wander for millions of years, then put it under our sun. You would expect it to turn on earlier and harder on CO2 than your average periodic visitor. That's exactly what we're seeing. CO2 brings its own physics. It sublimates easily and carries dust well. It also means the coma can become optically thick in a hurry. Think of it as a light-scattering shell that can boost brightness beyond simple surface area considerations. That's one plausible piece of the light curve overshoot. The object didn't suddenly get bigger. The effective reflective envelope did. Now the headline grabber, a sunward structure. The childish explanation would be gravity wrong or radiation pressure broken. The adult version, projection plus inertia plus size distribution. Fine dust behaves like a leaf in a windstorm. It goes wherever light pushes. Bouldery dust acts like a thrown baseball. It keeps the velocity vector you gave it for a long time, and radiation pressure hardly nudges it. If jets on the hot day side face ejected a lot of big grains more or less toward the sun, and you observe from a geometry that lines up those trajectories, you can get an anti-tail that points sunward in the sky plane, while the gas and fine dust do the classic thing downwind. It's not cheating, it's 3D. Add plasma to taste. Once you ionize the gas and charge the dust, the solar wind's magnetic field starts vetoing your naive arrows. Pick up ions, field-aligned flows, induced magnetators. Comets are messy electromagnetic laboratories. Under heavy outgassing, the bow shock and draped fields can corral dust into features that look like intent. No conspiracy required. The point isn't that the anti-tail is normal. It's that it is reconcilable without invoking aliens or new physics. Interstellar chemistry, plus a fortuitous aspect, can produce structures your intuition rejects if you only ever watched postcards of Halley's Comet in grade school. Let's talk about color without the superstition. Green can spook people because it screams signal in nature and culture. In comet science, green is just physics doing its thing. When sunlight's ultraviolet hits certain molecules, their electrons get kicked up and then fall back down, releasing light at specific colors. Diatomic carbon, C2, glows in a set of lines around the green part of the spectrum. Cyanide can add blue. Mix that with reflected light from dust, and in long exposures you get that ghostly emerald halo. The weird part with 3I/ATLS isn't that it turned green. Plenty of active comets do. It's when the switch flipped and how sharply the green ramped up. Early spectra leaned carbon dioxide heavy and light on obvious carbon radicals. So why did the emerald wash snap on near 2 astronomical units? 3 clean explanations. Threshold chemistry. Photochemistry has knee points. As heat and ultraviolet build, carbon dioxide cracks into carbon monoxide and oxygen. Organic residues start to cook. Diatomic carbon, C2, crosses a visibility threshold. Suddenly the green is obvious. Exposure geometry. A new crack opens and vents a carbon-rich layer. For a few rotations, you're sampling a local plume with a different mix than the average coma, so the scene looks greener from our line of sight. Instrument and processing differences. Filters, stacking choices, deconvolution routines, and even sky conditions during events like a lunar eclipse change contrast. One setup pulls out the green lines, another mutes them. The darker sky during an eclipse boosts the visibility of faint emission. Bottom line, once C2 shows strongly, carbon chemistry is awake. That's the whole point of studying an interstellar time capsule, to watch a different recipe light up under our sun, not just repeat the local script. If you wanted to irritate professionals, you'd schedule the most interesting changes for the exact weeks when Earth has to look away. That's the timeline. As activity rises, solar elongation drops. The Hubble Space Telescope and the James Webb Space Telescope have strict sun avoidance rules. Ground giants can push a little closer, but scattered daylight lifts the noise floor until faint structures drown. So we passed the baton to spacecraft that didn't sign up for comets. Mars Reconnaissance Orbiter has a camera meant for boulders. MAVEN sniffs atmospheres and plasma. ESA orbiters carry spectrometers tuned for Mars. None of them are ideal. All of them are available. If teams can point, track, and integrate long enough, we might catch high phase angle views that Earth can't get, revealing forward scattering from larger dust grains and clarifying whether that sunward anti-tail is big dust, charged dust, or both. Ultraviolet and infrared lines, less accessible from Earth at low elongation, pinning relative amounts of carbon dioxide, carbon monoxide, water vapor, cyanide, and diatomic carbon near peak activity. Solar-wind interaction clues from plasma instruments pick up ions, the standoff distance of the bow shock, and field draping that hints at conductivity and dust charge. Threading this needle requires brightness to hold, precision pointing to stick, usable Martian skies, and spare data budget. Manage expectations. A handful of frames and spectra would be a win. Size is still murky, and that's not just a joke about the coma. When the atmosphere around the nucleus is this fat, you're separating a point-like core from a glow using assumptions about reflectivity and viewing angle that may not apply to alien ice and dust. If you force a small, dark nucleus into the solution, you need higher gas output to match the observed brightness. If you assume a larger, brighter nucleus, you ease the gas budget but create tension with rotation physics. Bigger bodies don't spin up easily from vent thrust unless the jets are extremely lopsided. Rotation is the dog not barking. A clean periodic brightness wiggle would give a rotation period. 3I/ATLE has been too noisy, too constrained by geometry, or too close to spherical to cough up a simple answer. 2 live options. Slow rotator. Day-night temperature differences become brutal. Activity localizes on the lit face, and you get coherent sunward jets. That lines up with the anti-tail and the extra brightness at 2 astronomical units. Tumbling or nearly symmetric, the light curve smears out any period. Jets still happen from cracks, but rotation mixes stresses in weird ways that keeps fragmentation risk on the table. Tumbling plus venting equals strain. Internal structure is next. A high porosity interior lets heat sink deeper and wakes volatile pockets under a crust that a local comet might have already sealed. That explains sustained gas production after the initial jump and the oversized coma. It also sets up late-stage drama. If vents widen or merge, erosion can run away and split the body. When social feeds chase sci-fi, this is the anchor. Chemistry. A carbon dioxide heavy inventory turns on early and hard, swelling the coma and boosting brightness faster than water-first models expect. Grains. If the dust you launch is larger on average, inertia beats the gentle push from sunlight. Throw it from a hot dayside vent, and it coasts sunward long enough to draw a forward spike in projection. Plasma ionized gas and charged dust follow field lines and solar wind flows invisible in a single frame. Filaments and sheets are normal in a plasma, not paranormal. Geometry. We're viewing a three-dimensional spray on a flat canvas. Change the observer's angle and the same sheet draws a different arrow. Is there room for real novelty? Of course. That's why we study interstellar samples. If the sunward spike persists while the viewing angle changes, if the green intensifies while spectra don't show fresh carbon, if gas speeds exceed sublimation models, then we talk about surface superheating, phase changes in ices, or dust cohesion. We haven't calibrated for these mixtures, still normal science. No warp drive required. Here's the clean forward look, no fluff. Three outcomes cover most of the space. The Titan lung survives and stays loud. Bigger coma, multiple tails, green waxing and waning with rotation, water vapor finally taking a bigger share as deeper layers warm. Win long baselines for interstellar dust optics and volatile depletion. The quiet fade, the early burst was the show. By perihelion, the easy reservoir is spent. It rounds the sun, loses steam, and by December it's faint. Win direct limits on volatile inventory and how carbon dioxide-rich bodies throttle down. The shatter. Fragmentation. Heat stress or jet torque breaks it. We reacquire a train of fragments and a debris sheet. Jackpot. Layered composition exposed. Different gas and dust from piece to piece. A lab on internal structure. All three are useful. Only the last one sells posters. But any of them pays out scientifically. We can stare into the sun, but we can follow the breadcrumbs. Mars orbiter releases. If teams squeezed in off-pointing, long exposures, we'll see calibrated frames and maybe ultraviolet or infrared spectra that were impossible from Earth. Solar wind monitors. If this comet punches the heliosphere hard, pick up ion data and changes in magnetic draping will show it. Not TV-friendly, paper-worthy. Post-conjunction alerts. The first professional notes, after the blackout, will flag position, brightness and shape. If you read fragment, multiple condensations or fan structure evolved. Sit up. Color reports. If green persists or migrates around the coma, that's rotation plus chemistry. If it vanishes, we crossed and passed a threshold. Was there only 3 interstellar visitors in, and the variety is already wild. A shy, non-venting sliver, with odd acceleration. A loud carbon monoxide-rich snowball that was mostly normal, but chemically foreign. And now a carbon dioxide-driven fog machine, firing a sunward dust lance and flipping green early. The temptation is to mythologize. Don't. The real universe is stranger and more useful than any placeholder story we invent to fill an observation gap. Build this mental model. Planetary systems make small bodies across a wide range of temperatures, chemistries, and histories. Some get kicked out and wander. When one passes through, our job isn't to declare miracles, it's to standardize what looks miraculous until it's just physics again. The countdown to the Mars pass is almost over. The conjunction blindfold is almost on. Somewhere between those beats, 3I/A telas will reveal itself, fast burner, slow survivor, or brittle experiment, cracking under a star it has never felt before. If you're here for the unsweetened truth, we don't control the comet, we control whether we're ready. Ready means accepting that a sun-pointing plume can be real without being magical, that green is chemistry not conspiracy, and that sometimes the best seat belongs to a repurposed robot camera around another world, because that's the geometry the cosmos handed out. Rewind to the first flicker. A soft, offset smudge stepping across a Chilean starfield. The ATL's survey doesn't do romance, it does subtraction. Shoot. Wait, shoot again. Subtract frame 1 from frame 2, and teach a machine to care about what didn't cancel. Most flags are junk. Interstellar is never the default. It's what survives triage. First you fit an elliptical local orbit, then you hunt older images. If you're lucky, the ghost shows up weeks earlier in last month's frames. Link points, refit, and the math starts rejecting captivity. The energy goes positive. Residuals shrink. Someone finally says it out loud. It's unbound. Surprise 2 came early. A faint coma at a distance where locals are usually quiet. You don't need space glass to tell active from rock when the wings are fuzzy. Still, if you can point Hubble, you try. The first looks weren't wild, just a smallish core wrapped in a big for the distance coma. On paper, the labels are simple: third interstellar, comet by behavior, credit to Atlas. The real story lives in the spectrum, the light curve and the dust you sling into space. Early spectra lean toward carbon dioxide with water vapor not yet wearing the crown. Remember, the coma is a snapshot of what's being liberated now, shaped by sunlight and which patch is breathing. Even with caveats, the ratios were the kind of weird interstellar objects promise, not impossible, just outside our bell curve. Speed is bookkeeping. Fit the motion, run it forward and back. The number that matters is the hyperbolic excess. What speed it keeps after the sun is done. Imumamor was fast. Borisov was faster. 3I/Atlas is faster still. Why belabor the mechanics? Because it explains the tension in everything that follows. This wasn't born with a headline. It was an outlier that math convicted. Orbital mechanics is fair and merciless. Early October, Mars pass. Late October, perihelion. Early November, end of the blindfold. Late November, into December, reacquisition. We can compute the where and when. We can't negotiate better angles. Solar elongation steals signal. You can see stars in twilight, sure. But the last 30 degrees to the sun are a wall. The atmosphere scatters blue light and smears contrast. Even infrared gets hammered by a warm sky and a bright horizon. Adaptive optics fixes turbulence, not daylight. Space telescopes wear blinders for survival. Point too near the sun, and you roast what you can't replace. Result: the best tools for carbon dioxide-led chemistry will be on mandatory break at the exact moment the coma might do its strangest tricks. Mars is the loophole. High phase angles, different lines of sight. A triangle sun spacecraft comet that Earth can't match. The enemies are track rates and ops time. These orbiters were born to stare at ground, not chase a faint, fast target. But if even one sequence lands, a single clean spectrum resolving carbon dioxide, carbon monoxide, and water vapor near peak would rewrite a dozen models. One image of a sunward fan at a geometry Earth can't reach would settle a chunk of the dust debate. One ultraviolet detection of cyanide or C2 during the green onset would tie timing to mechanism. You don't measure visitors with the tools you wish you had. You measure them with whatever's flying when they show up. Saying half a solar diameter sounds scary. It isn't a threat, it's a diagnostic. And 3I/8LS is outpacing the simple heat budget models. Picture the coma as the sum of faucets. Each volatile has its own activation curve. Water's handle is stiff. Carbon dioxide's turns easier. Carbon monoxide can drip in deep cold. Cracks can open handles the sun alone wouldn't twist yet. The result is not a gentle ramp, it's a staircase. 3I/8 LS climbed 1. Gas expands in all directions at a few hundred meters per second. Dust rides it until sunlight peels off the fine stuff and inertia keeps the heavy fraction on ballistic arcs. Add a few jets and fans and you get a tangled time-variable density field. Change the viewing angle a little and the same coma looks different in every photo. Carbon dioxide complicates things further. Its sublimation steals heat efficiently, keeping surface layers cooler while still driving huge outflow that can delay water even as the coma balloons. To a playbook written on water-led comets, that looks wrong. It isn't wrong, it's foreign. Now the anti-tale. First, make it boring. Dust tends to hundreds of microns, across barely feel sunlight's push on coma timescales. Launch it from a dayside vent, and it coasts sunward for hours or days before radiation pressure and orbital motion redirect it. At small Earth-comet sun angles, the projection lines it up with the sun. No rules broken. Now add plasma. Photonized gas sees the interplanetary magnetic field. The field drapes around the flow. Charged dust starts following electric and magnetic pathways. Flows organize into filaments and sheets. Your eye reads intention. It's just electrodynamics. Takeaway: an oversized structured coma isn't a circus trick, it's a laboratory. Every gas speed, every dust size, every emission line is a handle on a nucleus we can't touch. Here's the blunt truth. The conjunction gap is not a nuisance, it's a hole. The weeks when gas should peak and dust structures should be most revealing are the weeks we can't look. Ground attempts at twilight will tempt you into bad photometry. Space telescopes will obey their rules. There are no rebels. So we rehearse reacquisition. Ephemerides ready, medium aperture sights cued to hunt where and when the comet should reappear. Reduction pipelines that compare apples to apples, same filters, same extraction apertures, same standards. Models pushed forward without retrofitting to imagined unseen events. We also talk like adults. Amateurs bring cadence and coverage. Pros bring calibration and precision. You need both, and we temper the headlines. The right posture is aggressive humility. Assume the comet will do something you didn't predict, and be ready to measure that, not the version that flatters your prior. Read the bulletins and abstracts, and you can feel it, focused, hungry, slightly rattled. The light curve's persistent overperformance isn't a one-night burp. The sunward feature isn't a processing ghost. The green didn't wait for perihelion. It snapped on early. None of that trashes physics. All of it says your priors were local. 2 traps to avoid. Calling a sustained trend an outburst so you can ignore it. Reaching for exotica because it makes a better story. A sobering side note. This is also a lesson for planetary defense style modeling. No 3I/8 LS isn't a threat. But when brightness, gas output, and dust transport can be off by factors because chemistry is off nominal, you stay humble when you attach confidence bands to unfamiliar close-pass objects. The optimism to keep the Rubin Observatory is coming. Cadence and depth will find interstellar visitors earlier and more often. This won't be the last blindfold. It can be the last one we enter unprepared. Mars orbiters weren't built to chase faint, fast comets. They were built to map rock, sniff air, and send home canyon shots. But a spacecraft is just a camera, gyros, and a computer. If anything can pivot for a day, here sits why it matters. High-resolution images. You won't resolve the core at tens of millions of kilometers, but you can integrate on the inner coma with rock-steady point spread, and at phase angles that boost forward scattering. If the anti-tail is a sheet of large grains, the surface brightness profile will show it. Near-infrared and ultraviolet spectrometers, separate carbon dioxide, carbon monoxide, and water vapor during peak. If you catch cyanide or diatomic carbon in emission, you timestamp the green phase precisely. Plasma packages. If outgassing is strong, you may see the comet's bubble in pickup ions or magnetic field draping. Constraints are real. Slews integration, downlink and pipelines not designed for faint movers, but a single clean sequence anchors the mid-gap and keeps us honest. Comets are foam. Porosity above 60% is common. That makes them great at storing volatiles and fragile under stress. The toolkit for tearing them apart is simple. Thermal gradients. Slow rotation bakes the day side and freezes the night side. Expansion and contraction pry cracks open. Vent flow cools its own walls and can widen those cracks. Venting torques. Jets act like thrusters. Asymmetry spins you up or down. Small bodies can cross into instability in hours. Bigger ones take sustained thrust. Tidal assists. At a perihelion beyond 1 astronomical unit, classic solar tides aren't the main killer, unless the body is already a Jenga tower. Interstellar aging, radiation, micro impacts can set that up. If it fragments, science wins big different layers, different mixes, different colors. If it survives, we still win. Depletion curves for carbon dioxide versus water vapor, dust sizes to compare with Borisov and locals, torque budgets that constrain cohesion. The only lose is the Hollywood one, a fade so hard that the September surge was the whole tank. Even then, we learn how much active area was required to hit that light curve. Here's the unsentimental next 35 days. 3I/80 LAs slides toward the sun. Ground photometry degrades as the sky brightens. Space spectra go quiet, because pointing rules say so. 1 or 2 Mars attempts either land and give us a thread through the dark, or miss and leave a clean gap. Perihelion happens anyway. The comet tears, flares, or shrugs. Then the angle opens, and we greet whatever comes out. That isn't defeat. That's the job. What matters is being ready the minute the curtain rises. Same filters, same reductions, same cadence, cool heads. If fragments sparkle, we'll read the layers. If one tired survivor limps out, we'll read the depletion. Either way, we learn something we didn't already know, and an alien snowball obliged. 3. I/8 isn't magical. It's worse. It's real. And it's breaking the habits we learned from homegrown comets. The light rose faster than it should. The coma swelled until it could swallow Mercury's orbit. Color flipped to an eerie green, and a stubborn plume keeps pointing toward the sun like a spear. None of that requires aliens. All of it requires humility. Tonight we're going to make this voice actor friendly. No alphabet soup. No unpronounceable symbols. Just the straight story of an interstellar object that refuses to read the manual. The Atlas survey in Chile doesn't watch the sky the way poets say it. It samples, subtracts, and flags motion. Night after night, a robot takes 2 pictures, subtracts one from the other, and highlights whatever moved. Almost everything it finds is boring. Satellites, near-Earth rocks, noisy pixels. This time, buried in the churn, a faint smudge stepped between frames. The software raised a hand. The humans checked the math. Here's the first filter they run, in human language. Step 1. Pretend it's local. Assume it's one of ours on an elongated but closed path fit an orbit. Step 2. Dig through older pictures from weeks back. If you're lucky, you find the same smudge hiding in last month's data. Add those points to the fit. Now the honest part. The more you feed the solver, the more the orbit insists on a truth you can't domesticate. It doesn't close. The energy is positive. The shape is open. The speed after the sun is done pulling will still be high. That's the definition of interstellar. That's the I in 3I. Almost at the same time, the images betray a second clue. The core isn't sharp and stellar. It's wrapped in fuzz. That fuzz is the coma, gas and dust turned free by sunlight. At that distance, most local comets are coy. This one was already breathing. Target of opportunity requests went out. Telescopes that could still point near the sun without risking hardware took a look. What they saw wasn't cinematic. Not yet. A compact nucleus, a disproportionate coma, and a spectrum that, even with lousy geometry, whispered carbon dioxide is leading the dance. Water is late to the party. The paperwork followed. Third confirmed interstellar object in human history. Credit to the ATALS system. Comet by behavior. Outsider by math. Headlines caught up as the light curve began to bend. We can predict where the object will be down to absurd precision. We can't change where Earth will be when it matters. Early October, it sweeps past Mars at roughly 30 million kilometers. Late October, it reaches perihelion, closest to the Sun, around 1.4 astronomical units. That's inside the average orbit of Mars, but farther than Earth. Sounds fine, until you remember how the sky works. It's not about distance, it's about angle. The angle between the comet and the Sun, as seen from Earth, drops into the red zone. The sky around the Sun turns into a floodlight. Telescopes lose. On the ground, scattered daylight eats your signal. In space, survival rules forbid pointing too close to the Sun. The best chemistry machines we own go off duty right when the chemistry turns wild. That is not conspiracy. That is engineering. Mars is the loophole. Orbiters there might get a shot. Different angle. Thinner atmosphere. Instruments that can, with enough stubbornness, be repurposed for something no one paid them to do. If brightness holds, they can snatch a few images or spectra in the days before Earth has to avert its eyes. If this is the theme of 3I/Las. The cosmos offers you truth on a schedule you didn't pick. Take it or miss it. Astronomers use magnitudes. A backward scale where smaller numbers mean brighter objects. Don't worry about the tradition. Just remember this. Drop 2 steps and you're roughly 6 times brighter. Drop 3 and you're about 16 times brighter. In mid-September, 3I/Atlas didn't glide down the slope. It slipped a stair. That doesn't happen because sunlight warmed a smooth surface. That happens because a lid flipped, a crack opened, a reservoir of frozen gas found a path to space. Now the crucial caveat. Comets are drama queens. Many will burst for a night and then act normal. The difference here is persistence. The excess held, night after night. New points stayed above the old predictions. That implies sustained outflow, not a sneeze. No, it doesn't mean danger. Closest pass to Earth stays safely far. The stakes are intellectual. When foreign chemistry turns on in sunlight, we understand. You calibrate your whole picture of planet formation against it. Let's talk coma. Imagine a tiny dark onion of ice and dust, maybe a kilometer or 2 across, wrapped in a balloon of gas hundreds of thousands of kilometers wide. That balloon is real. We've seen it in other comets, but this time the scale is obscene. Carbon dioxide dominates. Water vapor is present but not king. That tells you where it formed. In many star systems, carbon dioxide can freeze out where water stays vapor. If your nursery was cooler or your chemistry skewed more toward carbon, you make bodies that wake on carbon dioxide first and hardest. Carbon dioxide is an efficient thief of heat. When it sublimates, when it jumps straight from solid to gas, it drinks energy and cools the surface layer that is feeding it. That can delay water's turn even as it drives a huge outflow. The result is a coma that's huge, while the classic water lines are still gearing up. If you learned on water-led comets from our backyard, this looks wrong. It isn't wrong, it's alien and expected. Once you let Interstellar mean something, dust rides that gas. The smallest grains get bullied by sunlight and blown away. The bigger grains, think tens to hundreds of microns, the width of a human hair, have inertia. They leave the vent and keep going in the direction you threw them. If your hottest vents are on the day side of a slowly spinning nucleus, those ballistic grains streak sunward. From our angle, that writes a straight, sun-pointing plume. It looks like a violation of a textbook rule. It isn't. It's three-dimensional motion drawn on a flat sky. Put a pin in plasma too. When sunlight strips electrons off gas molecules, you get a charged soup. The solar wind drags a magnetic field past that soup, and the field drapes around the comet. Charged dust starts following field-guided paths and drifts you didn't learn about in middle school. Filaments and sheets appear. Your eye reads intent. It's just electricity doing what it always does, in a place we rarely get to measure. Mid-September, the color changed. In long exposures, the coma glowed green. That isn't mystical. It's molecular. Sunlight pumps certain molecules so their electrons hop up and fall back down, spitting out green light as they relax. In comets, the usual culprit is diatomic carbon, two carbon atoms bonded, which scientists call C2. Cyanide compounds can add a blue tint. Mix in dust and you get the ghostly emerald that makes people nervous. Why did 3I/Atlas snap green earlier than expected? Two honest options. One, threshold chemistry. As sunlight and ultraviolet light intensify, carbon dioxide breaks down into carbon monoxide and oxygen, and complex carbon-bearing materials start to crumble. Free carbon atoms meet in the coma and form C2 out in space, where the sunlight can pump them. Once that reaction network crosses a certain density and light level, the green ramps fast. 2. Geometry. A crack rotates into view, feeding a carbon-rich jet that our line of sight didn't sample before. Either way, the takeaway is identical. Carbon chemistry joined the show. That's what we came here to see. Yes, processing choices in amateur images can exaggerate color, but even after you subtract the Instagram factor, professional spectra still report the expected emission. The green is not a Photoshop sin. It's a sign that alien ice isn't just venting, it's reacting in sunlight the way physics says it should. Here's the part people don't like to hear. You cannot beat the sun with wishful thinking. As the angle shrinks, the sky brightens. Ground-based telescopes lose contrast. Space telescopes obey safety margins. That means the great questions: does the nucleus hold? Does it split? Does water finally surge? Does the green intensify? May be answered while our best eyes are deliberately turned away. So we get practical. We prepare the handoff. We ask Mars orbiters to try captures on the days they can. We write the reacquisition plan now, not later. We lock down our methods so we don't fool ourselves. Same filters before and after, same extraction apertures, Same standards. We publish model predictions now, with dates and numbers attached, so we cannot move the goalposts after the blackout and pretend we saw what we didn't. One more thing. We respect the amateurs. Their cadence night after night stitches together a story professionals with limited time on giant mirrors can't always tell. The data are noisy. The coverage is priceless. None of the spacecraft at Mars was designed to chase a faint object moving fast against the stars, but they have cameras, spectrometers, and plasma sensors. With creative planning, a few sequences could land. High-resolution images might not resolve the core, but at the right Sun-Comet spacecraft angle, they can see how the inner coma scatters light. If the sunward feature is heavy dust, it will brighten under forward scattering. That's a fingerprint. Near-infrared spectrometers can hunt for the signatures of carbon dioxide, carbon monoxide, and water vapor, ideally in the same window so there's no argument about calibration. If an ultraviolet channel can pick up cyanide or diatomic carbon above the thin Martian air, it pins the green phase to a timeline. Plasma instruments could detect how the outflow is interacting with the solar wind. That's subtle, but if it pops, it tells you how big the comet's bubble is and how charged dust might be riding magnetic fields into shapes we don't predict with gas-only models. Will any of that happen? Maybe. It depends on brightness, pointing limits, power budgets, and how generous mission planners feel. One clean spectrum in that window would be worth a month of cloudy nights on Earth. Comets break for three main reasons: heat stress, jet torque, and bad luck. Heat stress first. If the nucleus spins slowly, the day side bakes while the night side stays frigid. Material expands and contracts out of sync. Cracks grow. Vents widen. Flow increases, which cools the vent walls by stealing heat. Yes, the gas chills what frees it, making them brittle. Repeat that cycle enough times, and a block can let go. Jet torque. Next. Every vent is a tiny thruster. If vents are uneven, they spin the body up or down. Spin a weak object fast enough, and it sloughs off material at the equator, or it rips at a neck where two lobes meet. We don't have a rotation period yet. That's the coin flip. Slow rotation points to dayside jets that line up with the sun. Tumbling raises stress but can smear out the rhythm. Bad luck is last. A body that travelled for millions of years in deep space took a beating from radiation and dust impacts. It may be foam held together by hope. For such a body, you don't need tides from the sun to pull it apart. A crack in the wrong place at the wrong time will do. If it fragments, it's a scientific jackpot. Different pieces expose different depths. Gas ratios change piece to piece. Collars might diverge. That's an X-ray of an alien snowball without lifting a scalpel. If it doesn't fragment, we still get gold. How quickly does carbon dioxide fall off after the peak? When does water finally dominate? How big are the grains on the far side of the sun when radiation pressure had more time to sort them? The only bad storyline is the quiet fade where the September flare-up was most of the tank. Even then, we learn inventory, how much surface area had to be active to hit the light curve, and how thin the reservoir really was. What is certain? The path is unbound. This is the third true interstellar visitor on record. It is active at distances where activity means not just water. The coma is enormous. A sun-pointing structure has persisted across instruments and nights. The color flipped to green early enough to matter. What is not? We do not know the rotation period. We do not know the exact size and shape of the core. We do not know the deep volatile layering. We do not know how strong the crust is. We do not know the exact dust size distribution away from the sun-facing plume. We do not know if perihelion will light new chemistry or silence the show, where people fool themselves by forcing one simple rule for outgassing as a function of distance across a chemistry that clearly isn't simple, by pretending the brightness trend is linear when it just hopped a stair, by treating green as a yes-no switch instead of a signal that depends on density, sunlight, and camera choices. The cure is pre-registration in spirit, if not in software. Make the calls now, nail them down. Be ready to be wrong in public, cleanly. That is not a defeat. That is the work. 3 interstellar objects is not a sample. It's a warning that our sample is small. The next decade changes that a new observatory in Chile will scan the sky faster and deeper than anything we've had. It will find more interstellar wanderers earlier in their approach. That means longer, cleaner arcs, better chemistry before the sun gets in the way, and a chance to plan. It also means you should stop pretending models trained on a handful of local comets can predict strangers with confidence bands that look like law. Operationally, we need standing plans. When a hyperbolic object clears a velocity threshold, telescope cues flex. Instrument modes for faint, fast movers are not cobbled together in panic. They are ready. Mars and lunar orbiters get look outward checklists that don't require a month of paperwork, and professional teams stop treating community light curves like folklore. The continuity they provide is the backbone. The big mirrors are the spikes. This is not a scolding, it's a to-do list. The object itself wrote for us. Here is the blunt play-by-play you can voice without hedging. Over the next days, the angle to the sun shrinks. Photometry gets dirty. Spectra go scarce. Mars tries to help. Perihelion hits in late October, whether anyone is looking or not. The nucleus either holds, sheds, or fails. In early November, the angle begins to improve. In late November into December, we hunt it where the math says it will be. We take the first clean measurement after the blindfold, and we do not tell a just so story. We compare before and after with the same yardstick, and we accept the verdict. If it's a single, dim survivor, that is not boring. If it's a string of fragments, that is not apocalyptic. If it is a fat coma with a new tail architecture, that is not a miracle. It's data. We came for that, remember? You don't promise auroras and sky shows. This will never be a naked eye spectacle. You promise the real drama. A messenger from another star system walked into our lab. We asked it to perform under our lights, and it chose to improvise off stage. So we changed rooms. We borrowed a camera on a different world. We prepared to catch it on the other side of the sun with the same tape measure. You also do not dunk on impossible. The sunward plume isn't impossible. It's inertia. The green isn't spooky. It's carbon. The brightening isn't a miracle. It's a lid popping somewhere inside a frozen rock the size of a small mountain. You do get to end with stakes. Every time we meet one of these, our picture of how planets form and how small bodies evolve gets wider. If the galaxy is diverse, and it is, then our models must be too. 3i/ATLRs is not here to flatter the ones we already like. It's here to make us write better ones. Ending 1. The Titan lung. It lives. The coma thickens. Multiple tails appear. The green ebbs and flows with rotation. Post-perihelion, we reacquire a survivor that is tired, not dead. Your script It didn't defy physics, it exploited chemistry. We now have the cleanest record yet of carbon-led activity from an interstellar comet. Ending to the quiet fade. The early surge was most of the tank. It rounds the sun and slides down the light curve. Your script, the flare taught us inventory. We can now bound active area, gas speeds, and how quickly alien ice goes silent under our sun. Ending 3, the shatter. It breaks. We see a train of condensations and a sheet of dust. Your script. We just got a cross-section of another star's snowball. The fragments are not a tragedy, they are a gift. Have them all ready, swap in the truth. Do not backfill. Models built for planetary defense are only as good as the family of objects they learned on. No, 3I/ATLS is not a threat, but the fact that our brightness and gas production predictions can be off by large factors when chemistry changes should sober anyone who claims we can predict the behavior of any incoming body from a couple of early nights of data. That's not fear-mongering, that's professional honesty. The fix is already in motion. More visitors, earlier detections, better statistics, and humility baked into the code. The calendar is cruel and perfect. Mars gets a glimpse while we lose ours. The sun gets its private show, then the curtain rises again, and the object tells us what it became. Either way, the message is the same. The universe is not short of surprises. We are short of patience and preparation. This time we prepared. Now we wait for the only number that matters, what 3I/ATLS looks like when it comes out of the glare. If it's louder, we'll measure the chorus. If it's quieter, we'll measure the silence. If it's many, we'll measure the family dot. Either way, we'll have to rewrite something. We keep saying it brightened faster than models. Let's open the hood. A comet does not glow because the nucleus is bright. The core is charcoal dark, often reflecting less light than fresh asphalt. The light comes from dust in the coma, reflecting sunlight, and from certain gases that glow when sunlight kicks their electrons and they relax. Two levers matter most for brightness: how much gas you produce per second, and how efficiently that gas lifts dust into the coma. Gas production is a heat problem. Sunlight lands on the surface. Some is reflected, some is turned into heat that flows inward, some is consumed to turn ice straight into gas. That phase change steals heat, which cools the surface and slows further sublimation unless more energy arrives. On a smooth, uniform body, this becomes a gentle balance. On a cracked, layered body, it becomes stepwise chaos. You open a new crack, sunlight floods fresh ice, gas screams out, dust follows, and your coma doubles in short order. Dust lift is a tug of war. Gas rushing through pores and cracks pushes upward. Gravity and cohesion say no. On an interstellar object with weird chemistry, the dust-to-ice glue can behave differently than our local examples. If the glue is weak, big grains break free. If gas flux is high because carbon dioxide is leading, the push is stronger. The net effect: larger particles get lofted at lower sun levels than a water-led comet would allow. Larger particles reflect light well and stay near the nucleus longer. Hello, bright inner coma. There's a third lever we rarely talk about because it offends neat diagrams: texture. If the surface is fluffy, like a fairy castle, highly porous, low strength, then heat penetrates deeper and pockets of volatile ice can erupt from below the skin. Deep vents act like geysers, narrow throats, high speeds, collimated flows. That creates bright fans and jets. From far away, a single jet aimed near the line to the sun can read as a blunt, sunward horn. All of that reaches a tipping point around 2 astronomical units. If carbon dioxide is king, carbon dioxide sublimates with gusto. There, water vapor is late, so the gas engine turns on strong, while the usual water thermometer still reads not hot enough. That's how you get a coma that looks like late-stage activity, while water lines still whisper. If you want a short version for your audience, it brightened like a light switch because a crack opened and carbon dioxide did the heavy lifting. The dust it lofted was big enough to shrug off sunlight and coast toward the sun for a while. From our angle, that writes a spear. Let's do the geometry carefully. Imagine the nucleus as a nozzle. On the day side, sunlight heats a patch, gas escapes, dust goes with it. The finest powder feels sunlight as a push. It swings around and streams away from the sun into the classic tail everyone knows. The heavier bits, grains the size of smoke seeds and larger, do not care much about that gentle push. They obey the throw you gave them. If the vent points roughly sunward, and the nucleus rotates slowly enough that the vent keeps pointing there for hours, those grains will outline a thin sheet reaching toward the sun. Now add projection. You are not looking from above. You are looking from some skewed angle with the sun off to the side. That thin sheet of grains becomes a bright spike in the plane of the sky. If the Earth-Comet-Sun angle is small, that spike points at the sun in your image, even though in 3 dimensions, the dust will curve and fall back. What could make it last longer than you expect? 2 things. First, bigger grains than the ones you assumed. Second, electrical effects. Dust grains pick up charge in sunlight. The solar wind carries a magnetic field that drapes around the coma. Charged grains can drift along field lines, forming filaments that resist the neat push-away narrative. You do not need a new force. You need to remember that space is not empty air. It is a plasma with rules that most textbooks leave out of the comet chapter. There is a test you can do the moment we get post-conjunction images. Watch what the sunward feature does as the angle between Earth, the comet, and the sun grows. If the feature fades with geometry exactly as a ballistic sheet should, grain inertia did the trick. If it persists with a shape and brightness that do not track the angle change, charged dust and magnetic draping are doing more of the work. That is the lever an editor will love. We can tell which physics is winning by how the spear fades as the angle opens. Now the emerald glow, think of it as a chemical clock. When the coma is sparse and the ultraviolet light is lower, you can have plenty of carbon dioxide and still not see much green. As the coma densifies and sunlight strengthens, reactions cascade. Carbon dioxide breaks into carbon monoxide, and oxygen, organic fragments get cooked. Carbon atoms get loose, pair up into diatomic carbon, say C2, and those pairs light up green when the sun kicks them. Cyanide compounds add blue, so the appearance and growth of green tells you when the chemical switch flipped. That's not just pretty, it's diagnostic. If the green ramps while water vapor lines stay quiet and carbon dioxide stays loud, the reactions generating C2 are happening in the coma itself from carbon dioxide and organic fragments. If water vapor kicks up at the same time, then you opened different layers at once. A voice-clean way to say it. Green is the color of carbon chemistry waking up. It is not poison in space. It is a timeline. There's an even better test. Map the green around the nucleus. If it wraps the coma evenly, it is a volume process, reactions everywhere. If it follows a jet, it's a source process, one vent feeding most of the carbon fragments. Mars-side spectra, if any are captured, could lock this down. After conjunction, medium aperture ground telescopes with narrowband filters can do it too, if teams coordinate. We still do not have a clean rotation period. That single missing number is why every model forks into multiple futures. If the nucleus rotates slowly, the day side bakes hard, vents aim sunward for a long time, and the antitail geometry stays coherent. Heat stress becomes severe on the day-night boundary. Cracks grow, jet torques act in a persistent direction. Spin up or spin down can be dramatic. If the nucleus tumbles or spins moderately fast, the heating is more even. Vents sweep arcs. Features blur. Torques average out. Structural stress drops a bit. The price you pay is less collimation in the dust, which the early images did not suggest. That leans the table towards slow for now, but we cannot call it without a periodic light curve. There is one trick left even during ugly geometry: polarization. Light scattered by dust grains is polarized in ways that depend on grain size and angle. If you can get decent polarimetry before the sky becomes hopeless, a change in the polarization pattern can hint at rotation state even when brightness trends are messy. After conjunction, polarization again becomes a lever if the antitail persists. Let's build the branches cleanly for your delivery. 3 big outcomes, each with distinct tells. We'll phrase them as checklists. Outcome A. The Titan lung survives and stays loud. What you see after conjunction: a large structured coma, multiple tails, a still present green component that waxes and wanes with rotation. Water vapor lines finally taking a bigger share as deeper layers warm. The sunward feature fading as geometry opens but replaced by broader fans. What it means: high volatile inventory, cohesive surface, carbon dioxide led early, water vapor joined later. Dust size distribution is broad, with enough large grains to have drawn the spear, but plenty of fine dust feeding classic tails. The science bite. We get depletion curves for alien ice under our sun, dust optical constants for grains that did not grow in our backyard, and rotation-linked chemistry maps. Outcome B, the quiet fade. It used the tank early. What you see: coma smaller and fainter than September forecasts, water vapor still modest, green diminishing, sunward structure gone, a single softer tail. What it means: the early crack exposed a limited reservoir. The crust did not surrender much more at perihelion. Heat sank shallow, or the surface refroze and choked vents. The science bite: constraints on active area and true gas speeds. A clean negative result for late water vapor dominance, a cap on dust mass loss. Outcome C, the shatter fragmentation event. What you see: a string of bright knots along the track, a wide dust sheet, unequal colors from knot to knot. Maybe one lead fragment with a small coma and several fainter pieces. What it means: structural failure driven by heat stress and vent torques. Different fragments sample different nucleus depths with different volatile mixes. The science bite stratigraphy. Without a drill, you can finally say which layers contain what and how deep the carbon-rich zones went. When the angle opens in November and December, success will depend on discipline more than drama. Observers must use the same filters they used before conjunction. If brightness was measured in red and green bands, the same bands must be used afterward. That is the only way to compare results honestly and track color change. The same principle applies to apertures and standards. The circles used to extract light from the coma must not change, and calibration must be against the same standard stars. Do not try to improve the method mid-story. Consistency matters more than novelty. Narrowband runs should be scheduled wherever possible, because filters tuned to cyanide, diatomic carbon, and a dust continuum can separate gas from dust even on modest telescopes. Polarimetry, if available, will add another layer of truth, revealing grain sizes through polarization patterns rather than guesswork. The search for fragments must also be deliberate. It is not enough to point at the predicted center. The track must be swept carefully because fragments often lead or lag. Finally, teams must share raw and reduced data quickly. This is not about pretty pictures, it is about extraction numbers and methods. The first days after reacquisition will set the tone, and they must be done right. Your line to deliver to the audience is simple. The curtain rises, and the job is to measure first and explain later. If Mars orbiters manage even a single clean observation, it could reshape the story. The inner coma structure at high phase angle is especially valuable, because forward scattering boosts large grains. If the sunward sheet brightens strongly under those conditions, it means heavy dust is at work. If it does not, then plasma draping may be responsible. Near-infrared spectra will also be decisive. Carbon dioxide and water vapor have distinct signatures in the infrared, and their ratio near perihelion will lock down the chemistry. If carbon monoxide is also detected, that points to a deeper ice reservoir. Ultraviolet data are just as crucial because cyanide and diatomic carbon emit brightly in that band. If an orbiter captures those emissions, the timing of the green phase can be pinned far more cleanly than Earth-based telescopes could manage before conjunction. Finally, plasma instruments could detect shifts in the bow shock or pick up ion counts, revealing how large the comet's bubble became at peak. The framing for your audience is straightforward. A camera that usually maps Martian rocks took a day off and turned into an interstellar observatory, and one spectrum from Mars could be worth a dozen guesses from Earth. Dust may not be glamorous, but it quietly decides what we see and how long we see it. Fine grains, smaller than a few microns, scatter blue light efficiently and are quickly pushed away by sunlight, painting the classic tail before fading fast. Medium grains, tens of microns across, reflect strongly and linger longer near the nucleus. They are the perfect suspects for a sunward sheet because they preserve their original trajectory before radiation pressure pushes them away. Larger grains, hundreds of microns to millimeters in size, barely feel sunlight at all. They fall along the orbit, like gravel, and can create debris trails that photobomb the view months later. The clues come from comparing brightness with angle, color with distance, and polarization signatures. After conjunction, if we can capture a clean sequence of those three, we will know whether the spike was created by heavy dust, charged dust, or both. The payoff is larger than this single comet. Optical properties of dust from an interstellar body will feed directly into how we interpret dust disks around young stars, where scattering is often the only signal we can read. Get the grain physics right here, and we stop guessing elsewhere. The way to tell this story without hype and without draining the wonder is to be clear about what it is and what it is not. Do not promise sky shows. Say plainly that no one will see this comet with the naked eye, that it is telescope territory only. Then elevate the real drama. We are watching alien chemistry in real time. Avoid calling anything impossible unless you define the term. A tail pointing toward the sun looks strange because our eyes are flattening a three-dimensional spray into a two-dimensional picture. In three-dimensional physics, it makes sense. Own the blackout honestly. The sun will hide the comet during its peak, and that is not a conspiracy. It is simply the safety rule for billion-dollar telescopes. Name the predictions that can be tested, such as whether a dust spear fades with changing geometry or persists because charged dust is involved. Train the audience to listen for outcomes, not adjectives, and celebrate being wrong cleanly. If water vapor does not surge as expected, that is not failure. It is proof that carbon dioxide dominated longer than we thought. The right tone builds trust. And if you need a short, sharp closing line, no, it is not aliens. Yes, it is stranger than we expected. That is better. It must be said again, 3I/8LS is not a threat, but it is a mirror. The fact that our models can miss by factors when chemistry does not match local patterns should make us cautious whenever we reassure the public about unfamiliar close-pass objects. The correct message is not fear but humility. We have strong tools for the kinds of objects we have studied in depth, but for outsiders like this, we must learn quickly and adjust. The constructive takeaway is to invest in earlier detection, faster classification, and standing protocols for target of opportunity observations. That is how we shrink the unknowns before we face a case where the stakes are higher. Every interstellar object is a free sample return mission. The chemistry revealed in its breath encodes the conditions at the place and time it froze. Add enough of these visitors together, and you begin to map how planet factories across the galaxy arrange their snow lines and balance carbon against oxygen. Borisov showed that carbon monoxide can be abundant in some nurseries. Tu Monarmor suggested that some bodies travel dry or vent so subtly that we miss it. Now 3I/8LAS shows that carbon dioxide can lead strongly and early, and that dust behavior under that regime can defy our expectations. 3 visitors, 3 different playbooks. The message is not confusion, it is range. Planet formation is not a single recipe, it is a cookbook. The first clean night after conjunction will not sound dramatic, it will sound restrained. Observers will circulate telegrams with numbers, not adjectives. Position confirmed, brightness measured, sunward feature, absent or faint, cyanide weak, diatomic carbon moderate, waterlines weak or emerging. That is the music of truth. If fragments appear, the language will shift quickly. Multiple condensations detected, separated along the track, with different colors suggesting layered chemistry. Papers will follow, models will be humbled, and you will get to write the line we all want to write. We watched a messenger from another star crack open, and we read its pages. If it returns as one loud piece, the line is just as powerful. We learned how an alien snowball breathes under our sun for weeks without quitting. If it fades into a husk, it is still not a failure. We will have measured how quickly an alien reservoir can run dry, and that number matters.